So as we've just seen, a capacitor is also not just a store of charge, but it's a store of energy, because we can keep this LED glowing for some time after it's connected to it. Now, as you probably understand from GCSE, even nothing else, that potential difference, voltage, is work done per unit charge, and therefore potential difference times by charge is energy. So really, very simply, the area under a graph of Q and V is the work done, and therefore we can have a very simple, easy way to work out the energy in a capacitor, and you would just say that the energy E is a half Q times by V. Now, obviously, substituting this equation into it, we can replace VC for the Q, and we can say there's another version of it, which is CV squared. If we rearrange this to make V the subject of it, V equals Q over C, and we sub that in for there, we get the third and final version of this, which is a half Q squared over V. And so these are the three versions of the equation that tells us the energy in a charged capacitor. But I do appreciate some of you purist mathematicians out there would like to do a bit of calculus, so we're going to chuck that in there now. So we're going to arrive at this formula, this version of it, using calculus instead. Now, I'm no maths teacher, so bear with me if I use the wrong symbols and all that sort of malarkey. Anyway, here's roughly how it works. So we have our plates, as we know. There they are. And we're going to put our first bit of charge on there. So the first charge is building up, our negative charge goes on there, and some positive charge goes on there. So the first bit of charge that goes on, the first bit of DQ, if you will, that goes onto this plate, goes on very, very easily. Because once we've got a bit of charge in there, there's a potential difference and there's a field, so the next bit of charge goes on is a bit harder to push on, and the next bit that goes on is a bit harder to push on, and so on and so forth. And so if you think about it, what we've got to do is we've got to work out the energy required to push on all of these little bits of charge against the potential difference that builds up between them. So as this charge goes on, we get a potential difference across the plates, okay, and the work done, W, is going to be the sum of all the little DQs that are being added up against this voltage. Of course the voltage is changing, so we need to add it up, the DQs against all these changing voltages. Alright, so we already know that Q equals V over C, so Q equals VC, and V equals Q over C. So if we substitute this in for that, we can say, well, the work done, the total energy charging up this capacitor is going to be Q over C by dQ. Alright, now of course this is easy. Q by dQ is a simple thing to integrate, and the C is a constant, so we'll take that outside. The work done is 1 over C times the integral of Q by dQ. Now, of course, we're going to take this from some value, nothing, all the way up to, say, plus Q, whatever it is. And we integrate Q by dQ, and that gives us, what does that give us? That gives us Q squared divided by 2. Okay, and so we can say the work done is basically 1 over C, bring that back inside, Q by dQ. And so that gives us, so finally that gives us the energy of a capacitor. The energy stored in a capacitor is Q squared over C, and we normally put the half at the front, or 2C, so let's say 2C. And that is the precise equation that you get from doing it the other way. So energy in the capacitor, the easy way and the true way. Alright,